Points, lines, and planes. It all starts with a dot or a point. Now, get another point and connect both of them with a straight path, and you've got yourself a line. Now, if we line up an infinite number of lines next to each other, it gives us something known as a plane. It is a flat, two-dimensional surface, and it's where all the points and lines we've talked about live. But why stop there when you can have two planes? Slightly tilt one of them so that you can distinguish between the two. And because these planes are infinite, there is bound to be a certain part where they intersect. This creates an angle. An angle is what you get when two lines or planes meet at a point, forming the space between them. Think of it like an open book. Each page represents a plane, and the spine where they meet forms an angle. And depending on how open the book is, you get all sorts of different angles. If you just open it slightly, you get an acute angle. Continue and you'll eventually end up in a perfect L shape, commonly known as a right angle. And if you keep going, you'll end up in obtuse angle territory beyond 90 degrees. If you fully open up the book so that it's flat, you'll hit 180 degrees or a straight angle. And if you're psychotic, you will fully bend your book, getting you a reflex angle. But angles aren't totally random. They love to form all sorts of relationships. Complementary angles are like the socially awkward duo hanging out in the corner of a square room because they always add up to 90 degrees. If you've got one angle that's 30 degrees, its complementary angle will be 60 degrees. Supplementary angles, on the other hand, are like two sides of a seesaw balancing each other out to form a straight line. If one angle is 110 degrees, the other must be 70 degrees to complete the 180. We've also got neighbor-like angles known as adjacent angles. Okay. We've learned about points, lines, angles, but what happens when you start connecting those angles and lines to form something more complex? Well, your basic geometry gets a Pokemon evolution and turns into polygons. If angles are like the corners of a shape, polygons are the entire shape, with the simplest polygon being a triangle. You see, triangles are quite versatile, even in real life, being used in all sorts of complex structures like bridges, cranes, scaffolding, and a lot more. The standard edition vanilla version of a triangle is an equilateral triangle with every side and angle being exactly the same. Messing with both variables like a mad scientist gives you different forms of a triangle. Isosceles, scalene, and a right-angled triangle, which is as random as modern art pieces. Remember how angles had different relationships with each other? Well, so do triangles, which makes it extremely useful when trying to actually use them in real life for things like manufacturing or using maps to figure out distances in real life. The two main relationships are congruence and similarity. Now, let's dive into the world of congruence and similarity. Imagine you're at a party and you spot two twins wearing the exact same outfit. That's basically congruence, two shapes being completely identical in every way. But what if you see someone wearing a similar outfit, just in a different size? That's similarity. Same shape, different size. To prove triangle congruence, we've got a bunch of acronyms that sound like secret agent's code. SSS, SAS, ASA, AAS. These stand for side, 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 angle, angle, and angle, angle, side. If these match up in any two triangles, congratulations, you've got congruent triangles. Similarity is a bit more chill. We've got AA, SSS, and SAS. It's like that one chick who doesn't care about your size. But the thing is, triangles can get even more advanced when you combine angles and side together, giving birth to trigonometry. Trigonometry is all about connecting angles and sides in a triangle. Picture a ladder leaning against a wall. Sine tells you how high the ladder reaches, cosine shows how far its base is from the wall, and tangent is the steepness of the ladder. With trigonometric identities like the Pythagorean identity, which we'll get to, you can find missing sides or angles while the law of sine and the law of cosines lets you solve triangles. However, the world doesn't just revolve around triangles, so add another line to the mix and you get a totally new polygon. Just like the triangle, mixing around the variables gives you things like a rectangle, parallelogram, rhombus, and even this abomination, concave quadrilateral. You can keep adding more and more lines to get all sorts of shapes until you end up adding an infinite number of lines to get the ultimate shape, a pizza, commonly known as a circle. Cut that pizza through the middle and you get yourself a line known as the diameter, which is basically the length they refer to when talking about a 9, 12, or 15-inch pizza. Halve that line, and you get the radius, which can help you figure out exactly how much pizza you've got on your hands. Take that radius, double it, and multiply it by pi, and congratulations, you now know how to find the area of a circle. In fact, you can find the area of any of the different polygons that we just went over as long as you know the right formula. A circle has more than just radius and diameter. You can create a chord by moving around the diameter from the center, a secant by extending it outside the circle, and a tangent by touching the circle at one point. Adding two lines creates sectors or pizza slices with their own lines and angles. Circles also have unique rules such as central angles formed by two radii at the center and inscribed angles, which are half the size of the central angle formed at the edge when subtended by the same arc. Circles are cool because they are used to design objects like satellite dishes and antennas, but we need more theoretical ways to predict their movements, which is why circle theorems exist. They start combining all of these concepts together, like the one theorem that says angles subtended by the same arc are always equal, or the tangent secant theorem, which describes the relationship between the lengths of a tangent and a secant drawn from the same point outside the circle, which is literally the exact theorem that satellite dishes and antennas use to align their receptors properly. But these cool theorems and relationships that help out majorly in real life aren't just tied to the circle. One major polygon that has some of the most essential relationships in geometry is the triangle. We've already talked about right angles triangles. Well, some guy named Pythagoras figured that the L path in a right angled triangle sucked and realized going diagonally is much shorter. So he decided to come up with a relation known as the Pythagoras theorem. With this, you can pretty much figure out the length of any side as long as you know the other two. Seems useless right now, but let's visualize this. So far, we've been looking at all these points and lines in the middle of nowhere, and it would be much better to have some sort of reference for all this. That's where the Cartesian coordinates come into play. You get one central point known as the origin, and the further you go away from this point, the higher the value of the number that gets associated with it. Right now, we're in 2D, so we can either go horizontally away from the origin, also known as the x-axis, or vertically away, known as the y-axis. A combination of both of these gives you the exact space in which a point or plane is present. Now that we know where these points and lines exist, we can actually determine the distance between them by taking the difference between their x-axis and y values and throwing them into the line distance formula, which, if you actually look closely, looks a lot like the Pythagoras theorem, which it is. And this line between two different points isn't totally random. You can represent it using the equation of lines. There are different forms for it, like the general form and the point-slope form, but the most commonly known is the slope-intercept form, y equals mx plus b. The different variables in this equation tell you different things about the line, like where it crosses the y-axis or how steep it is. And for you OCD freaks who love to line things up perfectly, there is even a formula to calculate the midpoint between 2 points. Thank geometry for that. But why stop at straight lines when we can have curves? Geometry is filled with curves. Circles, ellipses, parabolas, hyperbolas, these aren't just fancy words to impress your math teacher, they're shapes that make our world go round. We've already looked at the circle, but conic sections take a step further by introducing a scary looking equation that basically just says that all points are the same distance from the center. An ellipse is what happens when you drop that perfect circle and deform it into an egg-like shape. Seems useless initially, but it is literally the shape that helps us figure out the different planetary orbits in space. Then comes the parabola, nature's favorite shape for throwing things under the influence of gravity. It's the path a ball takes when you toss it. Its equation helps us figure out the different parabola shapes and conversely the various path of airborne objects. And then there's the hyperbola, which looks like two parabolas had an argument and decided to face away from each other. But the world isn't 2D, so let's add another dimension. Squares turn into cubes, triangles turn into pyramids, circles into spheres, and a whole lot more bizarre combinations of 2D polygons to make 3D shapes. But we need ways to keep track of these bizarre shapes, so we've got properties like surface area, which is like measuring the amount of wrapping paper you'd need to cover the shape, and volume. That's how much stuff you can cram inside. Of course, all these formulas mainly depend on the exact shape, but they're quite similar to their 2D counterparts. For example, if you have a triangular pyramid, the surface area would just be the area of the triangle multiplied by the number of faces. Similarly, for a cube, it's just the area of 6 different squares added up. We don't just want these shapes to remain in one place, which is why we use transformations. These are like the shape shifters of the geometry world. We've got translations, which is just a fancy way of saying slide it over. Rotations, turn a shape around a fixed point, like a clock hand moving around a clock face. Reflections flip a shape over a line, like a mirror image. This concept is used in art and design to create symmetrical patterns. And dilations, that's when shapes decide to go on a diet or bulk up. Speaking of symmetry, it is when a shape can be divided into 2 identical halves. There are 2 types of symmetry. First off, line symmetry is when you fold a shape in half and the 2 sides match up perfectly, like a celebrity's face. While rotational symmetry is when you can spin a shape and it looks the same at certain points in the rotation. We can move things now, but to know which direction we're moving in, we need vectors. They're the arrows that tell us which way and how much. You can add them, subtract them, even multiply them by numbers. The whole concept of motion and force is built on vectors and their different operations. The dot product and cross product are fundamental operations between vectors with distinct outcomes. The dot product, denoted by a scalar value, measures the similarity between 2 vectors, representing the amount of agreement or projection of one vector onto another, whereas the cross product generates a new vector perpendicular to the original vectors. Geometrically, the dot product can be seen as a projection operation, while the cross product can be viewed as a rotational or orthogonal decomposition. Think of it like 2 friends either finding a common interest, dot product, or figuring out which place they want to go together. And remember those trigonometric identities that we discussed earlier? Well, they can be used to control a degree of these projections and directions. All these concepts come together when we tackle real-world problems. Optimization problems, for instance, use geometry to find the best solution under given constraints. This could be finding the shape of a container that holds the most volume with the least material, or designing the most aerodynamic shape for a car to maximize fuel efficiency. It's like playing Tetris, but with math. Proofs are like the court cases of geometry, where you have to present evidence and laws to make your case. These aren't new concepts, but rather a mental exercise to prove that everything in geometry actually makes sense and is real. There are various forms that proofs can take, including 2-column proofs, which present statements and reasons in a concise side-by-side format, and paragraph proofs, which use a narrative style to explain the reasoning. When constructing a proof, mathematicians often employ common strategies such as indirect proof, which is kinda like a detective proving a suspect's guilt by eliminating all other suspects, indirectly revealing the true culprit. Then there's proof by contradiction, which assumes the opposite of the statement and derives a logical contradiction, thereby proving the original statement. Kinda like if a person claims a restaurant is open 24/7, but you get there at 3 a.m. to find it's not open, proving the claim isn't true. Everything we've talked about so far falls under Euclidean geometry, named after the ancient Greek mathematician Euclid. But what if we change some of the basic rules? In non-Euclidean geometry, we play with Euclid's 5th postulate, which is basically about parallel lines. In Euclidean geometry, given a line and a point not on the line, there's actually only one line through that point, which is parallel to the given line. But these rules get thrown out of the window in non-Euclidean geometry, especially when looking at hyperbolic and elliptic geometry. In hyperbolic geometry, there are infinitely many parallel lines, and in elliptic geometry, there are no parallel lines at all lines eventually intersect. This may sound abstract, because it is, but they're crucial in understanding the nature of our universe. Einstein's theory of general relativity, which describes gravity as the curvature of space-time, relies on non-Euclidean geometry. The final stretch and far corners of geometry discuss topology. This is the branch of mathematics that doesn't care about size or shape, only about fundamental structure. To a topologist, a coffee mug and a donut are pretty much the same. They both have one hole. Sounds weird, but you need to think of topology as the study of shapes and how they can change without breaking. Imagine you have a stretchy piece of clay. You can twist it, stretch it, or bend it into different shapes. You can turn it into a ball, a donut, or a pretzel. In topology, these shapes are all the same because you didn't tear the clay or glue anything together. So, topology is all about understanding what stays the same even when shapes change in these ways. It studies properties that remain unchanged when an object is stretched, twisted, or deformed but not torn or glued. Remember, in the world of geometry, every point counts, every line has a purpose, and every shape tells a story.